Alright, how's it going, everyone? So, my name's Alex, and I think that I want to go over proof today with you guys. So, I'm doing a computer science subject, and it's hard. So I found out a way that I like to teach myself is teaching others. And so today we're going to go over the proof asking me to prove that the language, what we call LTM regular, is undecidable. Now, this is in the topic of Turing decidability. Very difficult. Right, so let's begin. First off, we let the language LTM regular be the set of all strings. I'll use this notation, left bracket and right bracket, such that L of M is regular. That notation means that we're looking at the source code of M, where that's just an encoding of the Turing machine in string form. Firstly, we've got to assume that to do this proof, we must assume that LTM regular is decidable. We do it by contradiction, right? And we'll call the decider that decides it, decider, in all caps, right? And we'll use decider to decide the acceptance problem. Now, the acceptance problem is the question regarding whether we can have some universal Turing machine, like a computer, for example, we can feed any other Turing machine, and it doesn't even have to run it. It can just tell it with a string, and it'll just tell us, oh, the string is in this Turing machine or not in the language of this Turing machine, right? It'll tell us whether the Turing machine we feed it, we give it, accepts or rejects, right? Call this accept. Now, accept shouldn't exist, right? That's the key. If we use the decider to make accept, that works, right? We know that accept shouldn't work, which means decider must not work, hence the proof by contradiction, right? We'll use decider to make some kind of algorithm that decides the acceptance problem, right? From a high-level perspective, this is what we're going to do. Accept, right? We're going to tackle that problem. So we have to feed in some kind of Turing machine, a source code of some kind of Turing machine, right? And any arbitrary string, W. We use decider and somehow, right? And then we'll return accept or reject if W is in the Turing machine's language or not in the Turing machine's language, right? And then in accept, we'll use the input TM, M, right? This Turing machine that will input, right, we'll make a mutant of it, which we'll call M prime. And we want to construct M prime in such a way that M bridges the relationship between the two listed variables, right? We have decider, right? Which, it's a double implication, right? Decider must accept the source code of M if and only if M accepts W, right? This isn't going to make too much sense right now. I'm sort of linking together weird topics, but you're going to see it in a second, right? Remember that we have three different paths that source code M can take, right? M could accept, reject, or loop, or diverge, right? We don't know what it's going to do. Accept should obviously accept. It should halt, right? Reject is going to halt reject. It should obviously halt. But loop is the difficult part. We don't know whether it's going to halt or not, right? So we need to be able to discern or identify, right? Decider, remember, will look at the Turing machine's code and decide whether the language in that TM, whether it accepts is regular, right? We can't tell if it's context-free, context-sensitive, whatnot, right? So we need to use this cleverly, right? We'll let decider be a Turing machine, LTM decider, regular, that decides LTM regular, right? So L decider, the language of decider is equal to LTM regular, right? And we use this machine to construct accept, which solves the acceptance problem, right? Now this is just the function call for accept in a really bad notation, right? So step one, we build a Turing machine M prime, right? So this is the function call, right? We have the source code M, right, which will be any Turing machine we want, and W, which is a string, right? And it's going to return true or false. It always stops. It's going to halt and return true or false, right? So the first step is we build M prime, right? It's a mutant of M, right? Now, M prime will take in any arbitrary string. M prime is just a Turing machine, right? You give it a string and it does something, right? It'll decide. It'll be yes or a no or diverge, right? But we shouldn't have diverging behavior. See why, right? First, we run M on W, right? Secondly, what we'll do is we'll have it go through this decision pathway. If M accepts W, right? And if X, well, remember this, that's X, is in this non-regular language, we return accept. Otherwise, we reject, right? And if M doesn't accept W, we reject. Now, this is the key, right? When we run M on W inside M prime, there's three behaviors that can happen, right? W will either halt M, like halt accept M, halt reject M, or loop, right? Let's tackle the accepting, the halting cases first, right? Let's say it halt accepts, right? It goes into this if statement, right? if M accepts W, it halts, right? Which means we can step forward to the next line of code, right? Over here, it accepts it, so it goes into here. Now, we'll test X, right? If X is in here, we accept, otherwise we reject, right? Essentially, what we're doing is we're accepting a non-regular language, right? Because M will only identify members of 0 to the n, 1 to the n, which is non-regular. That's context-free, right? We need a higher power than just DFAs or NFAs in order to recognize 0 to the n, 1 to the n, right? So, if M accepts W, M prime accepts by returning a non-regular language, right? By recognizing a non-regular language. It's kind of weird, but essentially what we've done is we've made it so that M prime will recognize a non-regular language when M accepts W, and a regular language when it doesn't, right? And you can see this here. When it halt rejects, it steps forward, it's not in W, so it moves to here. If M doesn't accept W, we reject. Universal rejection is a regular language, null set. It doesn't recognize anything, right? So if M doesn't accept W, and M prime will just return it'll only recognize the null set. So the language of M prime is going to be null set, which is regular, right? Now here's the tricky part, looping. If we run M on W and it loops, it's never going to step forward, right? It never accesses these two if statements, which means it gets stuck on this line. And if it gets stuck on this line, it never returns anything, meaning it recognizes the empty language, right? By recognizing the empty language, what we've done is we've also made it regular. So this one is paired to irregular, while these two are regular, right? And it's nicely summed up down in this table here, right? So if M accepts W, right, it accepts M prime accepts a non-regular language. If M does not accept W, it halt rejects, it accepts the regular language null set. And if M loops on W, it also accepts the regular language null set, right? M prime behaves completely differently. Right? We've made the source code for another Turing machine. We've written a Turing machine with a Turing machine. Now, here's the crazy part, right? We then decide to run decider on the input of M prime, right? So the output, sorry, of M prime, which is output. And with the source code of M prime, right? Using M prime source code, and we do that there, right? Remember, what decider does is it tells us if it's regular or not, right? So, if M accepts W, right, M prime starts recognizing a non-regular language. So decider rejects, right? And then what we do is we just reverse the output. Acceptance, right, accept, capital accept, should accept it, right? Let's look at reject. If M halt rejects on W, right, we accept a regular language with M prime, which means decider accepts, right? It's regular. So then we reject the output, right? We flip it. Finally, on looping, right, if M loops on W, right, M prime also accepts a regular language, recognizes null set, right? Which means the decider is going to tell us, oh, we accept it because it's regular, and then we just have to reject it. So do you see how we've mapped these three unique values into two, accept and reject? In a sense, we've made it so that we can decide the acceptance problem if we have the oracle power of decider. And that shouldn't happen. Hence, decider must not be decidable. We've reached a contradiction. The acceptance problem isn't decidable. We proved that with diagonalization before. That's why, right, the language LTM regular is undecidable.